Okay, good afternoon, Dr. Jensen here. Today we're going to look at quantum mechanics problems. So for a general chemistry class, this generally revolves around a variety of ways of tracking where electrons are. Okay, and one of the first ways that we do this is called electron configuration. Okay, so electron configuration is really a very simplistic counting scheme, right? So if we look at, say, an element like nitrogen, right? So when we want to write the electron configuration for nitrogen, right, it is a building up process. So everything starts from hydrogen. Okay, so hydrogen, if we look at the periodic table, all right, so let's look at the periodic table here, right? So so hydrogen, thing like right here, in the first energy level, okay, etc. So the numbers down the side of the periodic table indicate energy levels, okay? So each row, you can think of it kind of like an even more simplistic, right? Circular design or an onion design, right? So every energy level that goes up, every number on the periodic table adds a layer to our onion, okay? So everything starts with hydrogen, right? Which is the one, it's in the first energy level and it's in the s orbital. Okay, so the orbitals are designated by s, p, d, and f. Okay, in one of the lecture videos that we'll do later, we'll talk about what do those things mean if you want to know more detail about what those particular things mean. Presumably, we have some understanding of what the orbital values mean at this point, right? So hydrogen is in the first energy level, it's in the s orbital, and it's the first electron. Then helium is technically, if we're counting, is over here. So there are 2 electrons possible in the first energy level in the s orbital. Okay, the s orbital holds 2 electrons. As we read across, when we do electron configuration, we're just reading the periodic table left to right, just like you would sentences on a page. Okay, when you get to the end of the sentence, you start the next sentence. We'll read the sentence across, we start the next sentence, and we'll read the sentence across. Right? So there is nothing else. There is no p orbital in the first energy level, right? So their first energy level is over here and it's empty. So you start out the second energy level, right? So this is where we get our lithium and our beryllium over here as the s. So there's lithium and beryllium. So again, there are 2 s electrons present there. As we go across, then we get to boron, right? So boron will be right there. But boron's in the p orbital. Right? So it is still the second energy level, but now we're in the p orbital. Okay, nitrogen is also found over here. So we just want to count over until we reach nitrogen. So boron is 1, carbon is 2, nitrogen would be 3. Okay, and that would be the electron configuration for nitrogen. Okay, we can look at, let's take another one real quick. Here, let's look at sulfur. All right, so it's the same process. We start again at hydrogen, so 1s2, 2s2. So that takes care of my hydrogen, helium, lithium, beryllium. Over here to my boron, 2p. But sulfur's past this, so there are 6 total p electrons. So boron over here to neon, right? There are 6 electrons in the p orbital. And then we start a sentence again. So now we're over in the 3, in our 3s, okay? Now, my drawing is not quite accurate because my p orbital is down. My d orbital should be down a little bit here. But we go from the s, right? So from sodium and magnesium straight across to aluminum in the 3rd energy level, and then over to sulfur. So we want to count over from aluminum. So, or I'm sorry, I forgot my 3s2, right? That took care of my 2 electrons there. And then over to my 3p. And then we count over to sulfur. So then sulfur is the 4th electron in 3p. All right. So this would be the electron configuration for nitrogen and sulfur. All right. Now, another way that this is generally done is via an energy diagram. Now, generally, energy diagrams, if you're looking at this like on a quiz or a test, usually professors don't put out like the whole energy diagram because it eats up a lot of space. So what they do is they'll just take snippets of like the highest energy level. So the whole energy diagram will look like this. Okay, so that'll get us up to a 3p. All right, so that's about where we were for sulfur. All right, so let's look at what does the energy diagram look like for chlorine. Okay. So first, let's write the electron configuration. So it'll translate similar to here. Okay, 1s2, 2s2, 2p6, 3s2, 3p, and then we want to count over from chlorine. So chlorine is the 5th electron. Okay, and so when we translate this over to the energy diagram, what we're going to see is in the first energy level, okay, you see the orbital here. Each one of these little hash marks will hold 2 electrons, just like the s orbital, so that's why there's only one of them. So in the s orbital, there are 1 electron and 2 electrons. You'll always see these kind of designations where it's like a half arrow up and a half arrow down, and this is really looking at what's called the electron spin, which we'll talk about here as we get to the quantum numbers. So the 1s1 and 1s2, 2s1 and 2s2, 2p1, 2p2, 2p3. You're going to fill the up arrows first before they start pairing up because these are electrons. They don't want to be next to one another. So it would be incorrect to write up one and then down when there's still extra space, right? So usually I kind of refer to this as like the guys in a movie theater kind of seating where they're going to sit every other seat until there's no more seats, and then they'll start sitting next to one another, right? So there's 2p4, 5, and 6. Okay. Then my 3s1, 3s2, and then over to my 3p. So it's 3p1, 3p2, 3p3, 3p4, and 3p5. Now, generally on a test, usually they would just take this snippet here. They would just cut out this section and use this as the highest energy level to be represented. At least that's generally how I do it. Generally, when we look at whether they're energy diagrams or the electron configuration, there are generally only really 2 ways that these questions get asked, right? So here, if I give you, or you're given the element, right? The question is, what is the electron configuration? Or what is the energy diagram? Okay. Another way that we might see this is like this. Okay. Given this energy diagram, what element is represented by this energy diagram? Okay, so you have the question both ways. You have an element, give me the energy diagram. Here's an energy diagram, give me the element. So here we would go to the 3rd energy level, and since my p orbital is my highest one, I would count how many electrons are there, 1, 2, 3, 4, and we would go to our 3p, and we look for 3p4, which in this case, right, energy diagram. The other way to look at it would be also from the electron configuration diagram, where you were given this. And the question is the same. Okay. What element is represented by this energy diagram? Here we want to go to the last one. So in the 3s, we have sodium and magnesium. Magnesium is the second electron there, okay, the second one. So this is representing magnesium. Now, usually these are done in ground state, which means there's no excitation of electrons. The other thing to watch for is when given an element and we want to know, so if you're told like this is magnesium and you're given choices for what these are, oftentimes you'll see the choices where they look very similar, but maybe the electron configuration is written improperly. Right? And so people will, in a multiple choice question, say, okay, here's magnesium. Which one of these represents its electron configuration? It's like, okay, well, they both end in 3s2. Well, except for the fact that this is not a proper orbital orientation where I can have three. I can't have 3 s orbitals. So this one is wrong, right? And then this one is right. And so that's generally how multiple choice versions of this are represented, where there are several of these and some of them are not written properly. And so we have to watch for variations where it exceeds the maximum number of electrons possible within an orbital. Okay. Now, if we look back to our chlorine here, right? When we do the quantum numbers, right? There are 4 quantum numbers that are also can be represented here, right? Now, generally, in my class, I generally don't have people come up with the quantum numbers. Really, I focus on given the quantum numbers, whether or not those quantum numbers are allowed or not. So that could be one kind of question, is given the quantum numbers, which ones are allowed. If we were to come up with the quantum numbers for chlorine, you would essentially derive it using the orbital diagram here, okay? So let's look at how would we come up with the quantum numbers for this, right? This is the last electron, right? That's the one we're interested in. So the question is, what is the quantum numbers for that electron, right? So it's in the 3rd energy level, okay? It's in the p orbital, so when we're doing the quantum numbers, the p value is 1, s is 0, and d is 2, and f is 3, right? So it is in the p orbital, so the L value is 1. The m sub L is which kind of shelf is it on? And so here, this is again, the m sub L value is the orientation. It's like the x, y, and z coordinates. So it really just depends on what you want to call the orbitals. And right, remember that the m sub L ranges from negative L to positive L. So if my value for L is 1, the possible allowed values are negative 1, 0, and positive 1. So the value, since it's sitting on this particular shelf, I'm going to call this one the 0 orientation. Right? And it is the downward spin, so it is a negative 1/2. Okay, the spin only has 2 directions, right? So there are only 2 choices. It's either a plus 1/2 or it's a negative 1/2, which you can see in all of these directions here. It's either a plus 1/2 or it's a negative 1/2. Okay. This ranges from negative L to positive L. This here ranges from 0 up to n-1. And this one ranges generally from 1 to 7. All right, so that's it for our first look at quantum numbers. And we will come back a little bit later with some additional quantum number practice problems. And that is it for now.